So we're still in section 6.3, still talking about vectors. Just a couple quick points. We talked about some different forms of vectors. In your book, they'll list vectors with a capital letter. When we write them out, we'll write them as a letter with a little half arrow over the top. And we said that we could write vectors with the components. And we said this was the same as writing v1 I plus v2 j. And we said that our standard unit vectors, I was 1, 0, and j was the vector 0, 1. And what this tells us is if I have a set of coordinates here, whoops, let me go the other way. Just a quick sketch of what we're talking about here. If this is my x-axis and this is my y-axis, my vector v could be here. This is vector v. And what this tells me is that this side of the triangle is length v1 and that side of the triangle is length v2. So v1 tells us how far over we've gone, how far left or right. v2 tells us how far we've gone up or down. This form of the vector tells us exactly the same thing. And what these standard unit vectors, if I write those out, if I draw those, here's my x and my y. My standard vector, this would be x, like so, or this would be I, and this would be j. And it's just telling us we have a little vector pointing in the x direction with length 1, and a little vector with length 1 pointing in the y direction. So that's what these are telling us. So we can write our vector in component form like this, or using the i's and the j's. This just tells us how far in the x direction, how far in the y direction. And then our half sheet told us how we can add, subtract, multiply by a real number. And we also said that the length of v, and you'll see it written a couple ways, with the double bars or with the single bar, and that is going to be the square root of v1 squared plus v2 squared. That's the length or the magnitude of your vector. We said that vectors were equivalent if they had the same length or the same magnitude and they were pointed in the same direction. So it doesn't matter where they're located, as long as they have the same length and the same direction, they're equivalent. So geometrically, we ran out of time on Friday to talk about geometrically what we're doing when we're adding vectors. So let me talk about that really quickly. I'm going to say adding geometrically. And I just want to go over this really quick because it's really not that complicated. To add vectors geometrically, we place them head to tail. So if I have my vectors, here are my coordinate axes. And I'm adding two vectors u and v. So if this is vector u, and this is vector v. The vector I get by putting them head to tail is u plus v. So this is what, on those problems where it said represents geometrically what the operation was, basically what it was saying is that if we take vector v and put it right on if we place a tail of vector v on the head of vector u, and we connect those 2 points from the tail to the end, we get u plus v. And we subtract by placing them tail to tail. So if I have my vectors like so, and this is vector v, and this is vector u. The vector I get when I connect these endpoints is u minus v. And the reason that is, I'll draw another picture, and I'm going to just turn the direction of v around. So minus v is just the same vector as v but pointing in the opposite direction. So this would be u. And that would be minus v. So that's u. And that's minus v. And this is the same as adding these two together. Now they're head to tail, like I said up here. So that is u minus v. So when I add vectors geometrically, I'm placing them head to tail, and then connecting the tail to the head that I end up with. When I subtract, I place them tail to tail and connect the two, or I can flip the one around and then they're head to tail, and I have the subtraction. So this really was all those problems we're asking you was looking at the operations this way. But if you use the component form, what the component form is really going to be the more useful form, and the form that you're going to use most often to work with vectors. All right, questions on that quick recap? Okay. So we talked about the standard unit vectors I and j. But often we're interested in finding a unit vector in a particular direction. So we're going to talk about unit vectors in general. So that's our next. Unit vectors in general. And just as a reminder, we said a unit vector was a vector that had a length or a magnitude of 1. So we want a vector that has a length or a magnitude of 1. That's all a unit vector tells us. So if we want to find the unit vector in the same direction as some particular vector, say we have a vector pointing in some direction, and we don't want the vector to have a length of 7, we want our vector to point in the same direction but only have a length of 1. To find that, so if we have V, so V equals just some vector, a unit vector in the direction of V is, and we usually, I'm going to say U for a unit vector. U is the vector V divided by the length of vector V. Or the other way we can think of this is 1 over the length of vector V times V. So if I divide the vector by its length, that divides the length out of the vector, and I just end up with a vector of length 1. And because we're using vector V, our unit vector is in the same direction as vector V. So all we have to do to find a unit vector in a particular direction is divide the vector by its length. So let's look at an example of finding a unit vector. If we have vector V equals the vector 3, 4. We want a unit vector in the direction of V. So what we're going to do is divide this vector by its length or its magnitude. So the length of vector V is the square root of 3 squared plus 4 squared. We just square the components and add them together, take the square root, and we get the square root of 9 plus 16 equals the square root of 25 equals 5. So the length of vector V is 5. So our unit vector is going to be 1/5 times our original vector. And I can write that out as the vector 3/5, 4/5, or I can write that as 3/5 I plus 4/5 j. And if I were to go and find the magnitude of vector u, I would find that the magnitude of vector u, the length of vector u, is 1. So this is a vector of length 1 in the same direction as vector v. Now what if the problem had asked us to find a vector of length 10 in the direction of vector v? What could I do to figure that out? Anybody have an idea? Well, let me give you a hint. We found that vector u, and I'm just going to rewrite this together. So we said that u, which is 3/5, 4/5. The way we found u was we divided by the length of this vector. So the length of u is 1. That's what this process does. That's what unit vector means. The length of u is 1, and it's in the same direction. U is in the same direction as v. So if I wanted a vector of length 10 in the same direction as vector v, couldn't I just multiply this unit vector, this vector of length 1, by 10? This is a vector of length 1 in the direction of vector v. So if I wanted a vector of length 10 in the direction of v, so a vector with length 10 in the direction of v is just going to be 10 times my unit vector, which would be, if I multiply, that's going to be 10 times 3/5, 4/5. And if I multiply this through by 10, I get 6, 8. This is in the same direction as vector v. This is just 2 times this vector. And if I found the length of this vector, the length of this vector would come out to be 10. So to find the vector of any length, all I have to do is find the unit vector and multiply by whatever length that I want. So if the problem asks you to find a vector of length 5 in the direction of a specific vector, find the unit vector first and then just multiply it by 5. Multiplying it by whatever that number is going to give you that length. So this is how we find the unit vector. We just divide the vector by its length. And then to find a vector of any magnitude, we just multiply by whatever magnitude we want. So in your homework, you'll be given both kinds of problems. You'll be finding a unit vector and a vector with a specific length. They're really the same problem. To find the vector with a specific length, you just multiply by whatever length you're looking for. Questions on that idea? All right. Let's talk about how we combine vectors and a little bit of trigonometry. So we're going to talk about direction angles. Sometimes when we're working with vectors, we don't just have the x and the y components. We have its length or its magnitude and the angle that it makes with the x-axis. And we want to be able to work with vectors when we're given that information also. So if we're going to say u, and u is some vector xy. So u is a unit vector in standard position. And do we remember what standard position means? Starting at 0, 0. So u is a unit vector in standard position. That means it starts at 0, 0. So we have our situation looks like this. Here's my x and my y. And we have u. There's something wrong with this. So there's u in standard position. And we know that it's a unit vector, so that tells us that the length of u is 1. That's what unit vector means. And theta is this angle from the x-axis. and we're going to say the positive x-axis. So this is our situation here. We can write, if I draw in my little triangle here, what is the length of this side of my triangle? Using what we know about trigonometry, what would be the length of the x part of this triangle? On our unit circle, what gives us the x coordinate? Cosine. The length of u, the hypotenuse of this triangle, the length is 1, so this length is just going to be cosine theta. The hypotenuse of my right triangle is 1, so this is going to be 1 times cosine theta. What would be the y coordinate? Sine theta. So this little side of my triangle, since u is, the length of u is 1, is cosine theta. This side is sine theta. So I can write this as, we said u is the vector xy. Well, the x coordinate is cosine theta, and the y coordinate is sine theta. So if we know the angle, we can write the vector in component form. And we can also write this in terms of our i's and j's as cosine theta I plus sine theta j. So if we know this angle, we can write the components of our vector using the sine and the cosine of the angle. We call theta the direction angle. So if we know that angle, we know which direction our vector is pointing. It tells us how far we rotate around from the x-axis. And if we have some vector v that doesn't have length 1, if v is in standard position, v is, we'll say AB, in standard position, and theta is the direction angle, then v equals the magnitude of v times the vector cosine theta sine theta. And that equals, if I write it in terms of I and j, v cosine theta I plus the length of v times the sine of theta j. And the picture for this is exactly the same. What we have here is our vector like so. Here we have vector v that doesn't have length 1. Here's my direction angle. And I can just draw in the sides of the triangle. The length of the hypotenuse is the magnitude of v. So this side of the triangle is the magnitude of v times the cosine of theta, and this side of the triangle is the magnitude of v times the sine of theta. So if I have some vector, and I know the angle that the vector makes with the x-axis, I can write it in component form using the sine and the cosine of the angle of the direction. And if I have v equals AB and I want to figure out the direction angle, theta is the inverse tangent of B over A. Because looking at this triangle, from this triangle, tangent theta is opposite over adjacent. And this is the y component, and this is the x component. So if this is going to be A, this is going to be B. The tangent of theta is B over A. This is the y, and this is the x. Tangent of theta is just B over A. So if we're given our vector in this form, we can find the direction angle by using the inverse tangent of B over A. So let's look at an example using direction angle. And direction angle, just if you forget, if you're not sure, the direction angle just comes back to drawing your vector in standard position and using what you know about trigonometry on the sides of this triangle. So we want to find the direction angle for v equals 2I minus j. So first off, for this vector, what quadrant is this vector in? What vector does this quadrant point into? If I make a quick sketch, I'm going over 2 in the x direction and minus 1 in the y direction. So we're in quadrant 4. So this is a fourth quadrant angle. And we know that the tangent of our direction angle is the y over the x minus 1 over 2. If I plug that into my calculator, I end up getting that theta the inverse tangent of minus 1/2, and you should get about 333.4 degrees. Let's look at one more example using direction angle, and then we'll be done. Let's say we want to find the component form of the vector with magnitude 5. And a direction angle of 60 degrees. So this one, if you get a problem like this, this should be a really easy problem. The component form, our vector is 5 cosine 60 I plus 5 sine 60 degrees j. And does anybody remember from the unit circle what is the cosine of 60 degrees? One half. 5 halves I sine of 60 degrees. Square root of 3 over 2, j. So this vector would be 5 halves I plus 5 square root of 3 over 2j in component form. All we have to do is multiply the magnitude times the cosine of the angle, get my x component, and 5 times the sine of the angle to get my y component. Questions? All right. Homework. We're on page 436. There you go.